Okay, so in this last example that we're going to look at in section 3.1, we're dealing with one of those mixture problems. Remember, these problems usually come in the form of, a tank of some kind of solution with usually water mixed with salt or something else that can dissolve into water. And there's a concentration of that flowing, or there's a solution flowing into the tank. It gets mixed up, and we say it gets well mixed, which means the mixture is uniform. And then it gets pumped out of the tank, potentially at some other rate. And our goal is to come up with a function that determines the amount of salt or whatever the substance is in that tank at a given time t. And then we can use that to answer the question in this problem. So let's look at the specifics. We have a large tank. It's initially filled with 100 gallons of some fluid into which 10 pounds of salt has been dissolved. Okay, brine containing 1/2 or 0.5 pounds of salt per gallon is then pumped into the tank at a rate of 6 gallons per minute. The well-mixed solution is then pumped out of the tank at a rate of 4 gallons per minute. Find the number of pounds of salt in the tank after 30 minutes. It's important to note in this problem that the rate in and the rate out of this fluid is different. We have fluid flowing into this rate faster than it's flowing out. That means that the amount or the volume of the fluid in this tank is going to increase over time. It's not going to remain constant. We have to think about that when we come up with our answer. There is obviously the logical thing that you would ask here is, doesn't that mean the tank is eventually going to overflow? And the answer is yes. We don't know how large the tank is, how much time it would take for it to overflow, and that's not going to be important for us to consider to answer this question. We could phrase a question differently where that might matter, but it's not going to matter in this case. So the differential equation we came up with before for these mixture problems was dA dt. This was the amount of salt in the tank. That's what A represents, not fluid, just salt specifically. And that's equal to the rate of salt flowing in minus the rate of salt flowing out. Now, the rate of salt flowing in this case is constant because we're told that there is a concentration of 0.5 pounds per gallon in the solution flowing in, and that value is not changing. It's remaining constant, and it's also being pumped in at a constant rate. Now, when I say rate in, Rn, and I don't think I laid this out as clearly in section 1.3, so let me do that here. You can find that by doing concentration in. So what is the concentration of the fluid that's flowing into the tank times the flow rate of the fluid? I'm going to put the in out here. It looks a little confusing out there. Okay, so this is all of the fluid, not just the salt, right? And in our case, the concentration of salt flowing in is 0.5 pounds per gallon, and the rate of flow of the fluid is 6 gallons per minute. And so we end up with 3 pounds of salt per minute. That's how the units would work out. Okay, so a constant flow in, right? That's our R in. What is R out? R out is more complicated, and the reason for that, well, let's set this up. We need the concentration out. What is the concentration of salt that's flowing out of the tank times the flow rate of the fluid out? The issue with this one is that it's not going to be constant like it was in the previous case. The flow rate of the fluid is constant. We're told that the fluid is being pumped out of the tank at a constant rate of 4 gallons per minute, right? But the concentration of salt in that tank is changing because we're pumping pumping a solution into the tank and mixing it. So this will be constant, the flow rate of the fluid, but the concentration is going to be a function of T. So how can we make sense of that? Well, let's think about the concentration let's think about Yeah, I wrote concentration first. Let's write that first. Concentration is going to be the amount of salt in the tank altogether divided by the amount of fluid in the tank. So it's a ratio. It's the amount of salt divided by the amount of fluid, and that's how we would define concentration. What is the amount of salt in the tank at any given time t? Well, we know that that's a changing quantity, right? We know that that amount is changing. So the amount of salt is technically what our variable a represents in the first place. We can just call that a. What is the amount of fluid in the tank at a given time t? Well, that's not what a represents. Remember, a is just salt. So how can I determine the amount of fluid in the tank? We started with 100 gallons of fluid. And then we had this little conversation at the beginning of this video where we said we're pumping fluid into the tank faster than we're pumping it out. We have a rate of 6 gallons per minute flowing in and a rate of only 4 gallons per minute flowing out. The difference between these two, 6 minus 4, is 2. And what that means is that the volume of water in that tank is going to be increasing by 2 gallons every minute. So what is that? How do I use that here? Well, if we start with 100 gallons of fluid in the tank, and we're adding to that 2 gallons every minute, where t represents minutes, then 100 plus 2t is going to tell me the volume of fluid in the tank at time t. Dividing these gives me my concentration of fluid flowing out, concentration of salt flowing out. I also need to multiply that by my rate of flow, which we're told, again, that was 4 gallons per minute. Let's simplify this. This is the same thing as 2a over 50 plus t after doing some simplification. Okay, so I want to take these quantities, put them up into my differential equation that we wish to solve. dA dt equals rate in minus rate out. 3 minus 2a over 50 plus t. And this is an IVP as well because we are given an initial condition that we haven't used yet. A, the amount of salt in the tank at time 0, is 10 pounds. A of 0 equals 10. Let's try and solve this thing now. I'm going to take this dE and write it in a different form down here. I can write this as dA dt plus 2 over 50 plus t, I'll bring the a out front, equals 3. What I'm seeing here is that this is a linear dE that I can solve using integrating factors. Notice my p of t is this function right here. So my integrating factor, which we generally call mu, is e to the integral of that function, 2 over 50 plus t dt. That's equal to e to the power of 2 times the natural log of 50 plus t. And once again, remember, we don't need the absolute values here because of the context of this problem makes it unnecessary, right? 50 is positive. Time, we're starting at time 0 and counting up. So time will never be negative, which means this quantity will never be negative. So that means that I can solve this. This is the same thing as e to the natural log using logarithm properties, 50 plus t squared, or simplifying by canceling those guys, 50 plus t squared. I always run into this issue where my pluses and my t's look the same, so just be careful with that. So this is my integrating factor. I'm going to multiply both sides of my differential equation by that. That's going to give me 50 plus t squared dA dt plus 2 times, I don't need parentheses down there, 50 plus TA times 50 plus t quantity squared equals 3 times 50 plus t squared. I could do some simplification here, but I know that I don't really need to because the whole point of this is to resemble the result of the product rule. So all I'm going to do there is say that this is the same thing as d dt of a times 50 plus t quantity squared. That's all that we needed that for. And then this side is still 3 times 50 plus t squared. At this point, we want to integrate both sides with respect to t. And on this side, I just get a times 50 plus t quantity squared. On this side, I'm going to get 50 plus t cubed over 3, which will cancel with that 3, and so I get 50 plus t cubed plus some constant of integration, c. Finally, let's multiply both sides by 50 plus t to the power of negative 2 to cancel that out, and I get a, let's start calling it a of t now. A of t is equal to, this will do some nice canceling, 50 plus t plus c times 50 plus t to the negative second power. Okay, so I get this transient term here. All right, so we have that unknown constant c, and remember that's the job of our initial value to help us solve for that. So my initial value, once again, a of 0 equals 10. Let's plug that in and figure out what c is. So a of 0 is going to be plugged in here. That's equal to 10, so I can write 10 equals, I'm using my initial condition here. I know I've been writing that a lot, IC, for where I use my initial condition. That's equal to 50 plus 0 plus c times 50 plus 0 to the negative second power. This is easy to solve for c. That implies that c in this case is equal to, if you do all the work, you end up getting negative 100,000. I'm going to spare you all the arithmetic. I know you can do that without too much trouble. So that means that the function that we're looking at is a of t equals, remember this is a of t right here, but we figured out what c is. So this is equal to 50 plus t minus 100,000 times 50 plus t to the negative second power. That's our function. And the whole point of getting this function was to answer the question that we're given at the end of this paragraph. Find the number of pounds of salt in the tank after 30 minutes. Okay, so let's come up here and do that. What we want now is a of 30. Okay, so looking at our function down here, just plugging 30 in for t. This is equal to 50 plus 30 minus 100,000 times 50 plus 30 to the negative second power. And once again, all of that just goes into a calculator, and in this case we end up with approximately 64.375 pounds of salt. Okay, like I said, if there's more types of examples in this section if you read through the section, and I encourage you to do that, even though we're not going through all of those examples in this lecture video, and I'm not giving you homework on all those different types. It's still good to know because those types of applications will show up later in the course. But that's going to wrap it up for 3.1.